Okay, good morning, folks, or good afternoon, good evening, whenever it is you found time to watch this. Welcome to our first video. We're going to basically pick up right where we left off in Science 20, okay? And so before we had talked about ionic and molecular compounds. Now we're going to go what really the bulk of this first part of our chemistry unit is about is solutions, okay? So it's important to have an understanding of those ionic and molecular compounds from before. Now we're going to take those and look at how they apply when we talk about those things in solution. What does that all mean? Well, we've talked about it in previous science classes before, but it's been a while, I get it. So we will kind of do, you can see I've got some stuff here. We will get to it, but first we're going to kind of do an intro thing with some terms, definitions, and stuff so that when we come back to this stuff here, we can better contextualize what it is we're actually looking at, talking about, and maybe even why we're going to see some of the stuff that we're going to see when it comes to some of the solutions that we're going to make here. Okay, so to follow along in your notes, you need to go to page 6. Okay, so this would be the purple booklet that I gave out before school canceled. And if not, it's posted in the Google Classroom as well, a blank copy. Okay, so if you don't have access to a printer, do what you can, maybe take notes on paper while you have it open on your screen, whatever it might be. Okay, times are not perfect, so we'll do the best we can. All right, so I'm going to pull up the notes, follow along. Again, this is page 6. Okay, so once again, to just get started, we'll look at some of the important terms, things we need to know when we're talking about solutions so that we can make sense of the properties when it comes time to do that. So the first thing we're going to know is a solute. Okay, so the solute is the thing that gets dissolved in a substance, right? So that's the thing whose bonds end up broken by a solvent. Now, a solute can be a solid, it can be a liquid, or a gas. For example, if you make Kool-Aid, you know, you have the sugary powder or whatever, that's a solid. You dissolve it in a liquid, right? So in that case, the Kool-Aid would be the solute. It's what you're dissolving, right? Now, it can be a solid, it can be a liquid or a gas. So you can actually dissolve liquids in other liquids. For example, rubbing alcohol is a liquid alcohol dissolved in water, right? You can even have a gas. If you've ever had pop, you've been drinking a solution in which the solute was carbon dioxide, right? That's what it means for something to be carbonated. It's got carbon dioxide gas dissolved in it. So a solute can be a solid, a liquid, or a gas. Now the solvent, okay, that's the other kind of ingredient to make a solution. The solvent is the substance that does the dissolving, right? It breaks the bonds of the solutes and it's always present in a greater quantity, right? And that makes sense when we think about it. If I'm trying to make a Kool-Aid solution, I'm always going to have less of the sugar than I am of the water. If I keep pouring in sugar and sugar and sugar, eventually it's not going to dissolve anymore, right? It's going to be what we call saturated. It can't fit any more sugar in the water. Now, solvent can be a liquid or a gas. So if we go back to our pop, our solvent is obviously a liquid, right? It's pretty much just water that you add a bunch of syrup to, and then you dissolve gas in it. That would be our solute, right? But our solvent would be the water that we dissolve in it to make the pop. So solvent can be a liquid or a gas. However, you really can't have a solid solvent, right? Which makes sense if you think about that. How are you going to dissolve something in a solid? Grab something solid next to you, tap it, right? There's no way to dissolve something in that. However, a liquid or a gas, right? If we just air is actually, it's a solution. There's a bunch of stuff dissolved in that air. It's a bunch of gases mixed together. And so we can think of gases as also acting as solvents. Now, how do you keep these two things straight? Well, I like to use the trick, okay, of a solvent. Okay, there's a nice little, oh, that's way too big. There's a nice little trick here where we have that a solvent, okay, has a little V in it, and that's helpful. I don't know why this one is there, sorry. Solvent, the way I remember, see this V here, okay? Whenever we're dealing in Science 20, and honestly, 90% of the time, even outside of Science 20, or anytime we're making any kind of solution, really, our solvent is going to be water. Okay, there's a couple ways to think about it. What I mostly do is I say the V looks it's kind of pointy, right? It's got just like a W, it's got two pointy sides. There's also the fact that T, U, V, W, right? So V and W are right next to each other in the alphabet. So there's that way to remember too. V and W are right next to each other in the alphabet. So a solvent is usually water. Okay, so solvent is water. Now you can kind of remember that the solvent is the thing that gets, the thing that does the dissolving, right? So if we have a beaker over here with some stuff, okay, and we have, whoops, that's not how you draw a spoon. We have some spoon with some solute in it, right? We could drop the solute into the solvent, and we'll get to what we would make in a second here. But for now, let's just get those two straight. Solvent, solute. We dissolve the solute in the solvent. Okay. A little trick that might help you with solute as well. If you count the letters in solute, 1, 2, 3, 4, 5, 6, right? S-O-L-U-T-E. If you count the letters in solvent, S-O-L-V-E-N-T, there's one more in solvent. So it's a slightly bigger word, right? Well, we know that they're always going to be more solvent than solute. So bigger word, more stuff, how I think of it, right? Solute is a smaller word. So there's less of it. So less of it, right? There will always be less solute than solvent. You can never have more solute because you try it. Go make a solution of Kool-Aid and just keep dumping in more and more and more Kool-Aid. Eventually what you're going to do is end up with a pile of sugar coming out of your kind of wet glass of more wet sugar, really, right? It won't dissolve. Okay, so what do we get when we add a solute and a solvent? Well, a solution. Okay, so a solution, all that is it's a dissolved solute in a solvent, right? So once this solute goes into this solvent and it gets completely dissolved, what will we end up having? Well, if we are able, if they are soluble, right, if they do dissolve, then what we'll have is a solution where all the particles are actually completely, you won't be able to see them. So it won't actually look like that, and you'll see that in a second when we get back to our real ones, but I just want to give the idea that once we do both of those, we've made red plus blue makes purple, so that is our solution. It's just a solute plus a solvent, right? Solute plus solvent equals solution. Just an important note there on dissolved, you can't see the solute. That's important to know, right? So if you look at something like, you might be saying, oh, well, I don't know, salsa. If you make salsa, you can chop it all up and you mix it together. And hey, are the tomatoes dissolved in the jalapenos or whatever, the onions dissolved in the tomatoes? Well, no, because you can still point them out and you can see them, right? When you have a true solution, you actually can't see it. It will look uniform to you. Uniform meaning it looks the same everywhere. So we'll see that when we look at the actual solutions that I showed you at the beginning there. Okay, now here's our next two very important definitions. From the name, they kind of give away what they're about, right? It's nice. It's one of those science naming things that they did a good job. It makes sense when you read it. So electrolyte, okay? Electrolyte is just a solution, or sorry, a solute that when you dissolve it in water, right? So water in this case would be our solvent, right? We dissolve the solute in the solvent, and that when we do that, it'll make a solution. Solute plus solvent makes a solution. What makes the solute an electrolyte is when we make that solution, it conducts electricity, okay? Now, only certain kinds of compounds will make a electrolyte when you dissolve them. We know the type of compound that does it. For the most part, it is ionic compounds, okay? So they dissociate in water. Now, not all ionic compounds do this. Some are less soluble than others, but for the most part, we can think, okay, most ionic compounds will be electrolytes when you dissolve them, okay? So it splits up. If we dissolve it, what it means to really dissolve for an ionic compound is it actually splits up into the cations and the anions that made up the ionic compound in the first place. Remember, ionic compounds, they're made of ions. That's why we name like that. So they're usually electrolytes, and they can be tested with a conductivity meter. We will see that in a second here as well. We'll see if this is true, if this holds up. Okay, you've probably heard the word electrolyte before, and it probably came from Gatorade, right? Why does Gatorade have these electrolytes in it? Why would you want Gatorade to conduct electricity? Well, If you go right now and you wiggle your fingers in front of your face, right? Try it, wiggle them. What's doing that? It's electricity. It's electricity that's coming from your brain. Electricity is what tells your muscles to move. So you can think after a long hockey game, after a football practice, whatever it is, your muscles are tired, right? And they're kind of running out of that electrolyte that they need to use the electricity to move the way they do. So when we drink Gatorade after something like that, it can kind of replenish that and allow electricity to flow the way it needs to our muscles, the way we want it to. Okay, so Gatorade's the best known example, but there's tons, right? And we're going to make our own here in a second, actually. Okay, a non-electrolyte, like the name suggests, is a solid. When you dissolve the solute, it doesn't conduct electricity. So same thing, we take a solute, right? Dissolve it in a solvent, whether it's water or not, doesn't matter. And when we do that, it does not conduct electricity. Hence the name non-electrolyte. Okay, molecular compounds are usually the ones that are non-electrolytes, or almost always, molecular compounds are non-electrolytes because they don't contain ions. Remember, when we look back at how we were bonding, right? In an ionic compound, keyword ionic compound, ions were formed because electrons were actually transferred. Someone, for example, sodium, right, actually gave up its electron to chloride because chloride wanted to have 8 to have a full shell. Sodium just wanted to get rid of 1 to have a full shell underneath. And so we ended up with sodium 1 plus because it got rid of 1 negative electron, and we ended up with chloride 1 minus, right? And we have to remember when we're talking about those charges, what does that mean? It means electric charges. So when we put it into solution, let's just draw an electrolyte made with an ionic compound versus a non-electrolyte made with a molecular compound. Okay, so let's just draw one of each. I'll just draw the surface, okay, and I'll draw the surface. Now I'm going to pick NaCl for my ionic compound. Now ask yourself, why is this an ionic compound? So I'm still going to try and pause and get you thinking every now and then. But how do I know, and how would you know, that sodium chloride is an ionic compound by looking at that there? Okay, I'll give you a second to think. And then while you're thinking, I'm going to draw a molecular compound. And I'm going to ask you the same thing. How do you know that this C6H12O6, which is it's glucose, which is basically sugar, okay? This is a molecular compound. Now, how do I know that that's a molecular compound? How would you know that that was a molecular compound? So I'll come back to this one now. Sodium chloride. How did I know it was an ionic compound? Remember, well, we did this up here before, right? We said that it formed ions. Okay, great, but that's not much of an answer. It's an ionic compound because it formed ions. Cool, but what if I just gave you NaCl, right? I know that's an ionic compound because sodium belongs to the metals, right? The left side of the staircase, and chloride belongs to the non-metals, the right side of the staircase. And so that is a metal plus a non-metal. That's an ionic compound. Okay, you might remember that from earlier grades or from before, last week. Okay, so when I put sodium chloride into solution, into a solvent like water, I'm going to make a solution, is what I meant to say. Okay, so I put sodium chloride into a solvent, like let's use water, why not? That sodium and that chloride are going to split up into the cation and anion that make it up if they're soluble enough, right? So we're going to get sodium plus ions. We're going to get billions of them, but I don't have much room, so I'll just draw 1 and 2, okay? Now look at what's floating around in our solution. That's a bunch of ions, right? And remember, ions are electric charges, so it makes sense that this solution we've made here would be conductive of electricity. It would allow electricity to flow through it if we wanted it to, okay? So this is, sorry, we'll say that this is, if we look at it, our solution is full of charges. Not just, we throw that word around a lot, but let's stop and think about it, right? Charge means electric charge, okay? So it will conduct electricity. Full of charges. Where are the charges coming from? Well, Na plus, Cl minus, the ions, right? So it conducts. And let's use our new vocabulary here. What would we call this? An electrolyte. It's a solute that when we dissolved it conducted electricity. I'm just going to separate these a bit better because it looks almost like I'm talking about that one. Okay. Let's think about what happens when we put this glucose in there. So first of all, we got to think, what kind of compound is glucose? Well,
I asked you that before, and you might have been thinking, well, we did an ionic, so I bet this one's molecular, but great. What if I had just given you this one, though? Is it ionic or molecular? Well, look, carbon, is that a metal or a non-metal? It's a non-metal. It's on the right side of the staircase, right? Hydrogen, same goes for that. Oxygen, same goes for that. Those are all non-metals, okay? Quick note on hydrogen, you might be thinking, wait, that's not on the right side, that's not on the non-metal side of the staircase, and you'd kind of be right. It's in group one, right? That is because of how it can behave sometimes in reactions. This might be something you want to add to your periodic table in your data booklet. H, hydrogen, is really just, it's a non-metal that can sometimes act like a metal. So we kind of put it, it has the properties of, for example, one valence electron. So it kind of belongs in group one, but it really is a non-metal. Okay, so since these are all non-metals, we have a molecular compound. Remember, in a molecular compound, when that was formed, no electrons actually ever transferred. No ions were ever formed. So this thing never really had an electric charge to begin with. Everyone was sharing, right? Remember when I held out the marker and Julian held on to them back, and they were just sharing those electrons. So none of us ever got charged. I was never charged. Julian was never charged. We were just sharing electrons, right? So since there's no ions formed in the first place, there's not going to be any ions when you put it in solution. Okay, so this would spread out, it would dissolve, you would see it everywhere, but it wouldn't actually split up into any pieces. Okay, no charges. And so why are molecular compounds non-electrolytes? Well, because there's no ions. No ions in solution because there were none to begin with. Right? There were never any ions, so they're not going to be here now. That's a bit of an oversimplification, but that's not really. Okay, and so it will not conduct electricity because when we look at our solution afterwards, what's in it? Just a molecular compound and just some water, right? Water is not a good conductor, and you'll see that in a second here too. Okay, in the interest of time, we don't need to worry about these. You can think about them, they're good extension questions, okay? But for the time being, you can just, if you have your notes, scribble these out and we just won't worry about them for now. Okay, I'm gonna go back to the camera and we'll talk a little bit more. We'll actually look at some solutions in action. Okay, so here we are. We're back with our 4 beakers that we talked about at the beginning. Okay, so in here I have some sodium chloride, salt, right? So is that ionic or molecular? Answer that in your head right now. Glucose, ionic or molecular, right? And how do you know? And then we just have 2 beakers of distilled water. Okay, so I'm going to show you this thing. It's called a conductivity meter. Okay, so what you can see is if I hold it up backwards, see how there's a circuit kind of going all the way around, right? There's a circuit that goes all the way from the battery, which is essentially just a place to store a whole bunch of electric charge, right? And they don't want to really be near each other. We know from earlier science grade, opposites attract, like repel, so they would like to move around if they could. Okay, the charges in there. And so we have a circuit that's almost complete that would let them move, right? It would let them move, except that you can see on the very end there, that's part of the circuit, and there's a gap. It's broken. Oop, hard to point. Okay, there's a break in the circuit there. So what we could do is complete it with something that conducts electricity, and if that would happen, then on its way, the current would light up a bulb, right? So for example, metal scissors, those are a conductor. So those will, hopefully, there we go, right? That makes the bulb light up because now the circuit is complete. So all I'm doing is touching, and the circuit, since metal's a conductor, the electrons can flow now through the scissors and complete the circuit, and they light up the bulb very brightly, right? Because metal's a great conductor. Now, in distilled water, like I told you, distilled water is actually not a good conductor. You might see in movies and stuff where they touch water and they get electrocuted if it's nearby a live wire or something, but that's because distilled water, that's because that's tap water, right? Tap water is full of ions. Distilled water is not. It is very, very pure, okay? And so if I dip in there, you'll see I'm not a liar, right? Distilled water is not a good conductor. Notice nothing lights up, okay? Nothing lights up. Yeah. Okay, so no light in the distilled water. But what if, okay, we take and we make a solution? So remember, what are the 2 parts for a solution? You have to add a solute to a solvent. So we're going to use sodium chloride, table salt. Okay, just regular old table salt. You got this in your cupboard at home. Okay, we're going to add some table salt, solute, to our solvent, which is distilled water. Okay, you can watch me do it. So here I go. I'm just going to add it all. Notice how there's way more solvent than solute. We know that because that's always true, right? So it is there, down there at the bottom. Okay, now if I'm right and I can make a solution out of this, remember a solution, you shouldn't be able to see the solute when it's done, right? What I should see is it should look like a cup of water. But if I take a sip, I'll realize, oh, this is salt water. Okay, so instead of making you watch me dissolve this whole time, I'm going to pause the video. Trust me, okay, I'm not going to do any tricks, but when I come back, I'll have this dissolved. Okay, I'm also going to do the same with my other solute. That's going to be sugar. Okay, so what I'm going to do actually now is I'm going to change the label so I don't mess it up. But I'll make this one so you can see I'm not pulling any tricks. Okay, salt water. It's a saltwater solution. So we would actually say, see how it used to say solid? We would now call it aqueous. That just means it's been dissolved in water. Okay, and then I'm going to take this one, and this other cup of distilled water will be for making my solution with sugar. There we go. So this is going to get my sugar. Okay, and you can watch me pour it in. I'm going to pause the video, get them both dissolved because it takes some stirring, but once they're a solution, you shouldn't be able to see them. The only way you should be able to tell is through diagnostic tests, which we're going to do one of. Okay, so I'll pause it, we'll come back. Okay, so we're back. I've just mixed them up, dissolved them. Now you can tell, right? I'm not a liar now. When you look at the sodium chloride, that just looks like water, right? It's a solution. The solute has been dissolved in the solvent, and so it looks totally uniform everywhere you are. Okay, so that's my sodium chloride solution. And again, for my glucose solution, they look very similar, right? We dissolve completely different things in there, but once the solute has dissolved, okay, then we should see really no sign of it in there. It should just look like water, basically, right? That's true even when you make Kool-Aid. Now, the difference in Kool-Aid is you might get some color, but it's still going to be clear everywhere, right? So you can get colorful solutions, but they should still be uniform. If I were to keep adding salt, or I guess I'm doing sugar, if I were to keep adding sugar and keep adding sugar, eventually it wouldn't be able to dissolve anymore. There would be no more room in the solvent, right, which is our water. Okay, now there's a key difference between the type of compound that glucose is and the type of compound that sodium chloride is. So I asked you before, what type of compound is sodium chloride? What is glucose? We've kind of come back to that a few times. Well, we got a metal and a non-metal. Oops, it's backwards. We got a metal and a non-metal in our sodium chloride, right? Metal, sodium, non-metal, chloride. However, in our glucose, we have 3 nonmetals. So when we have a metal and a nonmetal, that makes an ionic compound. Since it's dissolved right now, we've got a whole bunch of ions floating around in there, right? And so our prediction would be, I'm just going to rinse off my conductivity meter. Our prediction would be that this would conduct electricity, right? So this is a good test. It's called a diagnostic test. It lets you figure out what kind of, if I were to forget to label these, right? How can I figure out what each type of solution is, right? So that's why it's always important to label your stuff, but we can run diagnostic tests on solutions to see what's in them. We could also, in theory, it's never a good idea and you shouldn't do it, right? To taste them, taste different. This would be salty, like Mr. Power when he catches you in the hallways. This would be sweet, like me, okay? So you can't taste chemicals though, because there could be a third one here that was hydrochloric acid, and if it was very concentrated, it might burn my throat, right? So don't never taste things in the lab. What we can do is diagnostic tests like a conductivity test. So let's test out our sodium chloride. Okay, so make your prediction. It's an ionic compound. Do you think it will conduct electricity and be an electrolyte, or do you think it won't and it will be a non-electrolyte? Whoa, very strong electrolyte. Okay, so all I've done to this water before that didn't even turn the light on is add salt, right? I just added some salt. And honestly, didn't even add that much. I could have added a whole lot more, right? And look at that. So now what is happening? Remember, this is a broken circuit, right? And so if something completes it, electrons do want to jump across, they just can't. They can't jump across through the air like that. But if there were something that conducted them well enough, they will make the jump, and then the circuit on the back would be complete, and they can make it all the way around, go through the light bulb, and light it up. Okay? So clearly, sodium chloride, when it's dissolved in there, is allowing it to do it. And we know that because of the ions that are in solution. Okay, cool. So I'm going to rinse it off, right? Remember, I got to rinse it off because now if I take it and dump it in the other one, I'm going to be mixing sodium chloride into it, and that's not good science, right? Now I'm mixing together different tests. Okay, let's try the glucose beaker. So in this one, I've just added glucose, again, a molecular compound, right? So there were never any ions present. They're sharing electrons. Nothing ever got a charge, an electric charge. So when we put it into solution, there's nothing to split up into for electric charges. So make your prediction. Do you think it will complete the circuit and allow electricity to flow? You can see that. I'm touching it in there. Nothing, right? Versus the other one where it almost blinded you. Okay, so clearly molecular compounds form non-electrolytes that do not conduct electricity. Okay, so to review, we have that we dissolved a solute, two solutes. We took our sugar and our salt, those were our solutes. We dissolved them in our solvent, which was water, right, to make two solutions. Okay, we took an ionic compound, sodium chloride, and we dissolved it in the solvent being water, okay, and it ended up conducting electricity very strongly because it split up into its ions, right? We took a molecular compound, glucose, we dissolved it in the solvent, water, right? So we dissolved the glucose solute in the water solvent to make a glucose solution, and that, because it was molecular and there are no ions to begin with, does not conduct electricity.
Okay, so the last important kind of definition I want to give really quick here before we move on. It's not too much. Once we've got the idea of a solute, solvent, and a solution down, this is just kind of one more idea, just a bit of an extension of that idea. And you kind of blew over it before, but you've actually seen it. We just made two of them, okay? And that's an aqueous solution. So when you hear that word aqueous, right, I think of like an aquarium or, I don't know, Aquaman, right? What do an aquarium and Aquaman have? Well, they like the water. An aquarium is full of water. Aquaman lives in the water. So aqueous, some people even say, an aqueous solution is just a solution in which the solvent is, you guessed it, water, right? So when we made our two solutions earlier with the NaCl, sodium chloride, and the glucose, C6H12O6, right, we made an electrolyte and a non-electrolyte, the electrolyte being the sodium chloride, the non-electrolyte being the glucose, right? So it was a non-electrolyte because it was molecular, no ions, which means no electric charges, right? Whereas in our ionic compound, it formed an electrolyte because it was, well, it's ionic. It's got electric charges in it, the ions, okay? So when we put them into water, when water was our solvent, that made an aqueous solution because water was the solvent. All right, so with that in mind, here's a little kind of look at what's going on. Why is water such a good solvent? Because it's got kind of a negative end and kind of a positive end. What that's really good at is ripping apart ions. Okay. Interesting to know, but not really the focus for now. So let's just kind of take this for the last thing for this sort of topic here. Let's try and apply it and see what we've learned. So these are some sample kind of test questions that you would normally see. So potassium nitrate, KNO3, okay, is considered a blank compound. So we'll be deciding between ionic and molecular. Well, let's just stop here. Let's answer one at a time. Let's kind of do our test skills. So KNO3. If this were ionic, it would be made up of metals and non-metals, right? As soon as you see a metal, game over, it's got to be an ionic compound every time, okay? There's no way to have a metal be involved in a compound and have it not be an ionic compound because the only way metals can form bonds is through the gain or loss of the loss of electrons, right? When you look at your periodic table, they all have positive charges. So they only ever lose electrons to form cations. And that's the only way they can form a bond. So as soon as there's a metal involved, game over. There's no way it's molecular. Okay, so C and D right away we can eliminate. This is
potassium nitrate. So it's KNO3 with the K being a metal, potassium nitrate being a polyatomic ion made of nonmetals, right? If you notice, NO3 will be on your periodic table. It'll be kind of in the top part, the table of polyatomic ions. You might remember those from grade 10, okay? Now, it's considered okay, we got that. We said it's going to be ionic compound. And when it is dissolved in water, H2O, it will produce ions. Okay, so they kind of gave us a hint there too, right? If it's going to produce ions in water, well, then it must be an ionic compound. How could a molecular compound dissolve to make ions? This means that it will either conduct or not conduct electricity. So let's think about that. It's going to produce ions. Remember, those are charged particles. And again, we keep throwing this word charged around. Charged means electrically charged, right? They're charged, yes, but that means electrically charged. So we have electrically charged particles floating around in the solution. That's going to be a solution that conducts electricity for sure. So we can actually eliminate B, and that kind of means A must be our answer, right? But just like our salt, our ionic compound, it conducted electricity when we tested with the conductivity meter. It lit up. And what does that make it? If it's ionic, it conducts. Well, it's an electrolyte automatically, right? So that kind of makes A, right? But that's the definition of an electrolyte, is something that conducts electricity. Okay, let's try the next one. Sucrose, C12H22O11 is considered. Now, first decision once again, is that ionic or molecular? So if it was ionic, it would contain at least one metal, usually, right? That's a pretty good test. So I don't see any metals. I see 3 nonmetals. I see carbon. That's a nonmetal. It's on the right side of the staircase. If you look at your periodic table, hydrogen, same thing. Again, it's in group 1, but that's more because of its 1 valence electron. Hydrogen, definitely a nonmetal. Okay. Oxygen, also a non-metal. So we got 3 nonmetals here. I'm thinking molecular. We can eliminate A and B. It's considered a molecular compound that when dissolved in water, H2O, does not produce ions. So there's no electric charges floating around. Okay, that means it will not conduct electricity, right? That makes sense. If there's no electric charges, the ions floating around, yeah, it's not going to conduct any electricity. We saw that with the glucose, right? And that makes sense as well when we look at what sucrose is. Sucrose is table sugar. Glucose is the sugar produced by plants. They're both really just sugars. Sucrose is a little more refined. It's what you have in your cupboard, probably. Okay. Making it, well, if it doesn't conduct electricity, that's just the definition of a non-electrolyte. Okay, so that wraps up section 1. Take a look at the questions we'll answer. Those are the big ideas for this topic that you should focus on having going forward. Okay.